I welcome you to the class of econometric methods. Myself, Dr. Muhammad Imdadul Haq, an associate professor at the Department of Economics, Aligarh Muslim University. Today, the discussion would be on the problem of autocorrelation. Autocorrelation is also referred to as serial correlation. See, one of the assumptions of the classical linear regression model was that the error term will not be related with its previous value. That is the expected value of ui, I stands for 1, and uj, that is the other error term. The expected value of ui, uj will be equal to 0. See, broadly, autocorrelation means when a variable is related with its or correlated with its previous values, but here we are exactly concerned with the correlation of respective values of the error term itself. So, this means that the value of the error term in time period t is not associated with its lag or forward value. If this particular assumption doesn't hold, then we face the problem of autocorrelation. And say we take a model wherein yt is equal to alpha plus beta xt plus ut. In this model, if we define ut as a function of a previous ut, a value that is ut minus 1, then we can say that ut is equal to rho ut minus 1 plus vt. Now this is the functional form. Now when this rho, it shows the degree of correlation between ut and ut minus 1. This is called as first order autocorrelation. Now if say means here the time gap is say between two values of an error term, like one in 2019 and the other in 2020, then it is called first order autocorrelation. And if there can be another case, if the time gap between the two values is 2, then we call it second order autocorrelation. Now we see what are the effects that if there is an element of serial correlation or autocorrelation present, then the OLS estimators which we had seen are blue. Those OLS estimators unbiased. The reason, the variance of the OLS estimators are underestimated. So when they are underestimated, this also will lead to the confidence interval will become very large. The moment the confidence interval becomes very large, the issue is significance testing gives problematic results. And in case if when your estimator itself unbiased and your significance testing is also not going in the proper way, then what we have is your prediction, which is one of the basic purpose of doing estimation, it also goes wrong. So hypothesis testing is an issue, and the unbiasedness of the estimator is another issue, because of which we need to be very careful about this problem. Now let us see as to why this problem happens. And before that, see, this is more common in time series data, where the data is ordered over time. And normally when we are working with say things like GDP and all this, now we have data from 1960 till 2022 or 23. So over the years when we have data in the time series format, it is likely that we will be facing this issue. Say, assume we have a consumption function. So now our theory says that consumption does not only depend upon income but also on wealth. But we excluded wealth. While estimating, we have taken only one variable, and that is income. So when this is happening, that is our actual model should have been yt is equal to alpha plus beta 1x plus beta 2 x2 plus ut, but we have excluded x2 variable in our case of wealth, and we have just included one variable, income. Then though we are saying that ut is random, that is which takes different values by chance and does not change in a systematic way, but if this first relationship is true, that is your consumption is depending upon both on income and wealth, then the then what will happen? Then this u will be taking account, this ut term, it will be taking into account x2 as well. That is, it will take into account, it will also be having within its within its purview, it will be also having this variable wealth, and it will then change systematically, and its value, the value of u will not be longer based on chance. This will be because a particular thing, wealth, is over there, and it is sitting over there in the error term. So this will lead to a problem of autocorrelation. So after excluded variable, the next reason why autocorrelation occurs is because of, see, the nature of the data. We have seen, or we know, that economic time series data, they move in a cyclical movement. They have a cyclical pattern. So they have a peak, they have a trough, and there is a period where it is falling down. Then again, there is a period where things are improving. So any feature, an important feature of these time series like GDP is these cyclical movements. They move from recession to recovery. Now, in this upswing, say we are going from recession to recovery, in this upswing, the value of the series at one point is greater than its previous value. Like we have something like this. We have, now we know that this value is, when it is going, this value is higher than this. So therefore it is probable that successive observations are not independent. Next one, we take, and another reason could be that we include a lagged value of the dependent variable as an explanatory variable. Like you take the case of our consumption. Our consumption is, present consumption is depend upon, it is the present level of consumption expenditure is not only influenced by the current income, but also by the immediate past consumption expenditure. Like in this equation, we have Ct is equal to alpha plus beta 1 Yt plus beta 2 Ct minus 1 plus u. Ct is your dependent variable, that is the consumption expenditure. It is also present as an explanatory variable with a coefficient B2. Now, in the above equation, in this equation, if the lag term is neglected, the resultant error term will show a systematic pattern due to the influence of lagged consumption or even current consumption. The reason being, again, if we are not including, if in our model we are not including our past consumption pattern, then that past consumption pattern will somehow impact the error term. So we cannot say that the error term is completely independent. Then another thing could be misspecification of the model. See, if you visualize a cost curve or a marginal cost curve, it is something like this. It is a marginal cost curve is like this. So it is not like a straight line. It is not like a straight line like this. Rather, it is a thing. So for this case, you need to incorporate a quadratic term, because there are two. One it is decreasing, and then again the slope of this line is increasing. So if we have specified, so the model, the correct model is this, where you are incorporating an square term of the output. But if you have taken a linear function, you have just saying that, okay, no, my cost function will be just like this. Again, this particular thing, it will be sitting in the error term. This again will lead to the problem of autocorrelation. Another case, normally it is with reference to agriculture, we can say the Cobb phenomenon. In agriculture, this supply reacts to price with a lag of one time period, because supply decisions take time to implement. The farmer plans his crop based on the previous year's price. So Y, that is the supply at time t, it depends upon previous year's price. Now, suppose at the end of the period, this price for today is less than the price of the last, then in the next period t plus 1, farmers may decide to produce less than what they did in the current period. So again, such type of things could lead to a problematic error term, and this could end up with the problem of serial correlation, or as we call it, autocorrelation. The next reason could be misspecification of the true error term. That is, see, random factors like COVID, war, drought, strikes, they all exert influence that are spread over more than one time period. Such cause result in a serially dependent values of the disturbance term. This cause of autocorrelation may be also called as true autocorrelation because its root lie in the error term itself. So, if this error term, the misspecification of the error term could also lead to the problem of serial correlation or autocorrelation. Next, we move to the types of autocorrelation. There are basically two types. One is called as positive and the other one is called as negative. We can identify them by simply plotting the residuals. Like we have drawn the 4 quadrant. Now here, what is the on the x-axis we have et minus 1 and the y-axis we have et. So the et axis is being extended to the negative domain, and et minus 1 is also extended to the negative domain. Now, upon plotting the error terms, if we find that these things are falling in, this is the first quadrant, this is the first quadrant, second quadrant, this is the third quadrant and fourth quadrant. If we find that the error terms are falling in the second and fourth quadrant, this can be said to be a case of negative autocorrelation. Let's see how a positive autocorrelation occurs. Now here the error terms are falling in the first and the third quadrant. If that is the case, so in most of the points et minus 1 fall in this quadrant, then it is positive autocorrelation, since the product of et and et minus 1 are positive. Another way to find out whether this is positive or negative is simply by plotting et against time. Here it is time, here we have time, and here we have et. No, so if the error terms in successive period change frequently, positive, negative, like this. So this we can interpret as a case of negatives autocorrelation. So when the variable goes upside and reaches peak point and again it starts falling without any time lag, then again it rises up. This is called as a case of negative autocorrelation. Whereas now this example is a case of positive autocorrelation. Here we have time, here we have the error term. So if the successive values of error follow a sort of trend line, that is several positive values are followed by several negative values, it is called as positive autocorrelation. Here the variable goes upside and falls slowly, taking a time lag to come to the negative zone, is called as. So this is an example of positive autocorrelation. In practice, autocorrelation is generally, like in macro time series data, in the autocorrelation is positive in more cases, and the reason for this is like economic growth and this cyclical movement in the economy. Most of the economic variables tend to grow periods of growth with periods of downturn, so they are cyclical in nature. So this is one of the most common thing over there. Now, so this was a crude method. Now how to test for autocorrelation? To test for autocorrelation, the most common thing used is DW statistics, or what we call as Durbin-Watson statistics. But we should take care that Durbin-Watson statistics is applicable only for first order autoregressive scheme. If we have a second order autoregressive scheme, Durbin-Watson statistics would not work. But still, it is one of the most basic things. Now here we have that we have written that equation yt is equal to rho ut minus 1 plus vt. So ut is the population disturbance term and rho ut minus 1 is the sample residual. Now here the null hypothesis, rho is equal to 0, and the alternate hypothesis is rho is equal to not 0. Now here rho is equal to 0, which implies that there is no first order serial correlation. We don't say that there is no autocorrelation, but we say no first order autocorrelation. And if the null hypothesis is there is first order autocorrelation. If it is a second order autocorrelation, then the same equation is modified and we have an additional term over here. But the moment if you have identified that your autocorrelation is of the second order, then we cannot use Durbin-Watson statistics. We have to go for the other method. We do a small derivation which we are showing you. Durbin-Watson statistics is equal to summation of Et minus 1 whole square divided by summation Et square. Now this is, if it's not clear, then either Et minus 1 whole square divided by summation Et square. Now this is the upper term is, this is nothing but a minus b square. This we can modify as a minus b square. So we write it at summation Et square plus summation Et square Et minus 1 square minus 2 summation Et minus 1 divided by summation Et square. Now for a very large sample, we assume that we are taking a large sample, Et and Et square and Et minus 1 square, they will be approximately the same. So if they are the same, what we do, we write it as, we simply write this also in this term. So in place of Et minus 1 square, we write it as again another Et square term. So 2 Et's minus 2 summation Et minus 1 divided by summation E square T minus 1. Now what we are doing, we are just opening up the things. So upon doing that, we can write it as we can be written in this format, that is 2 bracket open 1 minus summation Et minus 1 divided by summation Et minus 1 square. Now rho, we defined this particular thing as rho hat. So D can be approximated as 2 1 minus 2 bracket open 1 minus rho hat. Now rho is nothing but summation Et minus 1 divided by summation Et minus 1 square. Now see, there is a rule of thumb which says that the value of Durbin-Watson, the value of Durbin-Watson statistics will range from 0 to 4, and the rule of thumb is if it is 2, then it's not a problem, because when it is 2, the rho hat becomes 0, and if it is between 0 and 2, then we say it is a positive. This is a rule of thumb, not exact thing, but we have this. It is 0 over here. It is 2 over here. So in case of no problem, it is 0 over here and it is 4 over here. If it is between 0 to 2, we call it positive autocorrelation. If it is between 2 and 4, we call it negative autocorrelation. So if rho hat is plus 1, there will be a positive first order autocorrelation, then D tends to 0. If rho hat is equal to minus 1, then there is a negative autocorrelation and then D is equal to 4. So if the value, if rho has a value, because it's a correlation basically type of thing between two, it has a value, it ranges from minus 1 to plus 1. So if the value of d is equal to 4, it means rho is equal to -1. It is a case of negative autocorrelation. And if the value of d is equal to 0, rho is equal to +1. That is, it's a positive autocorrelation. And this 2. So if the value of d is equal to 2, rho will be equal to 0. If it is 2, then if it is rho hat will be equal to 0. So it is 2. Likewise, you can say. Then what we do, we tab the tabulated value of t we given in the table is the calculated value of d is obtained from this formula. Then we have another thing. We are there is a limitation of it that dw was not able to derive the full value of d. We got only the upper and lower limit calculated of the d table values. We will look at it. Now you can see over here, we have this du, t, 4 minus du, 4 minus dl and the dl. So this side it is for negative autocorrelation and this side it is for positive autocorrelation. So the first thing says, if the calculated value of d asterisk, the calculated of what you get is less than dl, is less than dl, that is d is less than dl, it means it exhibits positive autocorrelation. If d asterisk, the second one, is greater than 4 minus dl, 4 minus dl greater than over here, it means it's a case of negative autocorrelation. It is negative, it is positive. Third, if d asterisk is greater than du, d asterisk is greater than du, but d asterisk is less than 4 minus du, means this region, then this is a case of no autocorrelation. Now next, if d asterisk lies between dl and du, that is the this scene which is shown as the dotted, then this is called as inconclusive. The test is inconclusive. Here Durbin-Watson doesn't help. Again the same thing, if d is between 4 minus dl, it is greater than 4, it is less than 4 minus dl and greater than 4 minus du. Again the test is inconclusive. So H1 will be accepted when d lies between du and 4 minus du, and further in case of inconclusive result, the test will be rejected. So there was a limitation to Durbin-Watson statistics. One of the limitations are that we have some inconclusive zones. In this inconclusive zones, your Durbin-Watson statistics will not be able to tell whether it is a positive serial correlation, a positive or negative autocorrelation or serial correlation. There is another, so rough idea we have already got, that is when it is a positive, this side is a positive, this side is a negative. We have got an idea to that. So what it's saying, if it is d asterisk is less than du, if it is less than du, it is a case of positive. If it is more than 4 minus du, it is a case of negative. Now here in this example, what we are showing you is that we are taking an example of how the calculation of dw is done. Suppose we have a variable x and a variable y. We do the calculation of b and a. We know the formula of beta, that is equal to summation x minus x bar y minus y bar divided by summation x minus x bar square, and the formula for alpha is equal to y bar minus beta x bar. By using this formula, we get the value of a alpha. I have written here a is alpha, and you get the value of beta, that is equal to 2. Using this information, you calculate your estimated y, that is y hat. Now once you have calculated y hat, I have got, like I have shown as an example demonstration, it is 3. 3 is your intercept plus 2 the slope multiplied by x is 1. We get a value of 5, and likewise we get all these values. Now you need to calculate ET, that is the error. This is nothing but y minus y hat. Then we have done the calculation, all the, like it is 5 minus 5 0, 10 minus 7 3, 5 minus 9 minus 4, and likewise. Next, we do the step for et minus 1. This is nothing but you take and lag it by one time period. So we have this, then we do et this column minus this column, et minus 1. There is no calculation over here, hence there is no calculation over here. Now here it is 3 minus 0 is 3, minus 4 minus 3 is minus 7, and likewise you do the entire calculation. Next time you simply do the square. You take this and multiply with again with the same term. So 3 multiplied by 3, 9, minus 7 multiplied by minus 7, 49, and likewise this is calculated. And in the last column we have done the calculation of et square. This is your et, you simply square it. 3 square 9 minus 4 square 16, and likewise. Then we do the summation of this column, we do the summation of this column. We have seen the formula. The formula says it is summation et minus 1 square divided by summation et square. We use this formula. Here you get 76. Your dW is equal to 76 by 30, that is equal to 2.53333. This is how you can calculate the Durbin-Watson statistics. Although we have used Durbin-Watson statistics, but we should be careful. Things first, it can be used only for first order autoregressive scheme. Second, there are inconclusive zones wherein we will not be able to say whether there is a positive or a negative serial correlation or not. And this again, another demerit is, if there is if there is a lag value of the dependent variable is present as an explanatory variable. That is, if you have yt is equal to alpha plus beta 1 xt plus beta 2 yt minus 1. Now the lagged value is present as an the dependent variable is present as an independent explanatory variable in the lagged format. In this case, we will not be able to use the Durbin-Watson statistics. Next, we will go for, there is a we will go for another method, but here there is a trial and error method is also there. The trial and error method is a way wherein we go for different, we are going for different values of rho. Here it is, here rho 1, we take rho square, here we take et minus 1 whole square, here we take 1 minus et minus 1, here we have taken 2 et's. So what we do, what we are doing over here is, we are experimenting with the error term. We are taking different forms of rho. Then so there can be a third order or the fourth order autocorrelation also. So what we do, we will estimate all these and find the rho hat for each and also find the R square for each. Then we will conduct the significance test. Then given the significance, on the basis of R square, we will choose which of the following is the best. If R square is maximum, then we will find that rho hat is also significant. And the R square is maximum and we say that the rho hat is also significant, then we will be taking that to be as the best method. Okay, now we move on to the next method. Because we have seen in Durbin-Watson statistics there was a major issue, and that was, it was not applicable when, if a second order autocorrelation is present, we were not able to do it. We were not able to test using a Durbin-Watson test. So we have a Brish-Godfrey test which can be used in such cases. Now what we do is, we assume, we are just extending it. Suppose the disturbance term is written in a general format where ut is equal to rho 1 ut minus 1 plus rho 2 ut minus 2, continue till this is ut minus p plus et. Now here we go by regarding these error terms. Here we go by the assumption that expected value of Et is equal to 0 and the expectation of Et minus 1 when S is equal to 0 is sigma square, and when S is not equal to 0 it is simply 0. Now here we have the null hypothesis that H naught rho 1 is equal to rho 2 is equal to rho 2 is equal to rho 3 is equal to rho p extending, and this is all of this is equal to 0, which implies that all the autoregressive coefficients are simultaneously equal to 0. That is, there is no autocorrelation of any order. Now, what is the process is, that is what we do in order to do this this test. What we do is we regress on all regressors in the model plus one additional regressor, where the latter are lagged values of the estimated residuals in step 1. See what we do, we run the OLS regression and obtain the residual. So thus if say your P is equal to 4, if P is equal to 4, we will introduce 4 lagged values of the residuals as additional regressor in the model. For example, say in the case of two variable regression model, we have to run this regression, that is mu t hat is equal to beta 1 plus beta 2 x1 plus rho mu t minus 1 plus rho 2 mu t minus 2 extending up to rho t minus p. Then we obtain the R square. Here, see, if the sample size is large, this Bushfree got if the sample size is large, then this BG test has it will show that n minus p multiplied by R square, it can be approximated by a chi-square distribution, where here see what is P is the number of lagged residuals which we are including, how many lagged residuals we are including. This is asymptotically, that is n minus p multiplied by R square, that is obtained from this is step 2, follows the chi-square test with the p degrees of freedom. If in application p degrees of freedom, then we can say that if in application the calculated value of n minus p, that is R multiplied by R square, the critical value of this chi-square at the chosen level of significance, we can reject the null hypothesis, in which case at least one of the p, when we means if we reject the null hypothesis, this means at least one of the row is significantly different from 0. So I quickly repeat this method of BG test. First we run the OLS regression and obtain the residual. Now we regress on all regressors in the model plus one additional regressor, where the latter are lagged values of the estimated residuals of step 1. We calculate this, then we estimate this equation, we obtain the R square, and then we do n minus p multiplied by the R square. This is your BG test, and p is the number of lagged residuals are included. Then chi-square distribution is again your it's a right tail test. So if your value, if it falls over here, your null hypothesis is rejected. Null hypothesis is rejected means there is autocorrelation. So this is a method this is a method to detect the presence of autocorrelation, particularly when it is not of the first order, but it can be of the second order or the third order autocorrelation. With this, I end this lecture. In the next lecture, we will be taking up how to solve for the problem of autocorrelation. Thank you.